Welcome to Academic Math. In this video, I will solve question number 5 of the book Higher Algebra by SK Mapa. And in the previous videos, we have already solved the previous questions. And in this video, I will solve question number 5, 6 and question number 7. These three questions. And these questions are from exercise 2. And question number 5, it is given that a set S which has 4 elements A, B, C, D and rho is a relation defined on S. And we have to show that the relation rho is reflexive, symmetric but not transitive. Here is the question number 5. A set S is given by 4 elements A, B, C, D and relation rho on S is defined by A, B, B, C, C, D, D. A, B, B, C, C, D, D. A, B, B, A, B, C, C, B. A, B, B, A, B, C and C, B. B, C and C, B. These are the ordered pairs of the relation rho. Since A, B, B, C, C and D, D are all belongs to rho, therefore rho is reflexive. As by the definition of as x, x belongs to rho for all x belongs to S. This is the definition of reflexive relation, hence rho is reflexive. Now here AB belongs to rho implies that BA also belongs to rho and BC belongs to rho implies CB also belongs to rho and therefore rho is symmetric. To check rho is transitive or not, here AB belongs to rho and BC belongs to rho, but it is clear that AC does not belong to rho. That is AB A is related to B and B is related to C does not imply A is related to C. Hence the relation rho is not a transitive relation. Therefore, we have already completed question number 5. It is done. Now our target is question number 6. In this question, it is given that a relation R is defined on S. S contains 4 elements 1, 2, 3, 4. Question number 6. S is given by 4 elements 1, 2, 3 and 4. And a relation R is defined on S by and a relation R is defined on S by 1, 1, 1, 2, 2, 1, 1, 1, 1, 2, 2, 1, 2, 2, 2, 2, 3, 3, 3, 4, 4, 3, 2, 2, 3, 3, 3, 4, 4, 3. 3 4 4 3, and the last one is 4 4. These are the ordered pairs of R. These are given, so that R is an equivalence relation. We have to show that R is an equivalence relation. Our question is R. We have to show that R is an equivalence relation. By the definition of equivalence relation, we know that a relation is said to be an equivalence relation if it is reflexive symmetric or reflexive symmetric and transitive. As it is clear that 1 1 2 2 here 1 2 3 4 belongs to the set S. 1 1 belongs here, 2 2 belongs here, 3 3 these, and 4 4. That is 1 1 2 2 3 3 and 4 4. These are all belongs to the relation R. Hence, these all belongs to the relation R. Hence, R is reflexive. R is reflexive. Symmetric. To check the symmetricity, 1 2 here 1 2 belongs to R. 1 2 belongs to R. Here 1 2 belongs to R, and 2 1 is also belongs to here. 3 4 belongs to this, implies 4 3 also belongs to this. As 1 2 belongs to R, and 2 1 is also belongs to R. 3 4 belongs to R, and it is clear that 4 3 is also belongs to R. That is, we can say that if AB belongs to R, this implies that BA is also belongs to R. For all AB belongs to SF. Yes. Now, this implies that R is symmetric. Therefore, R is symmetric, R is reflexive. Now we have to check that R is transitive or not. Here 1 2 belongs to R, 1 1 and 2 2 also belongs to R. That is, 1 is related to 1 and 1 is related to 2, implies 1 is related to 2, and 1 is related to 2 and 2 is related to 2, implies 1 is related to 2. These two elements are same, these two elements are also same, and therefore by the definition of transitivity we can say that R is transitive. This is also true for the element 3 4 and 4 3 also. Here 3 4 belongs to R such that just a minute. Sorry for the interruption, it's raining outside. Here it is given that 3 4 belongs to R and 3 3 and 4 4 are also belongs to R. That is 3 is related to 3 and 3 is related to 4, implies 3 is related to 4 and 3 and 4 3 also belongs to R. 3 is related to 4 and 4 is related to 4, both implies 3 is related to 4. These two terms are same, common terms, and these are two common terms. Hence, in any cases, for all the elements of R, we can say that R is a transitive relation because for any ABC belongs to R such that A is related to B and B is related to C, implies that A is related to C. That is, if this and these two are happened simultaneously, then it will happen that A is related to C. Hence we can say that R is transitive. Therefore, here we have already get that R is reflexive, R is symmetric, and finally we get R is transitive. Therefore, we can say that the relation in R on S equals 1, 2, 3 and 4 is an equivalence relation. Now I will solve question number 7, that is question number 7.1. This question. So you have already seen that R is an equivalent relation. So our question number 6 is completed. Now in question 7 is given that set S be is a finite set containing two elements. S has two elements. How many defined binary relations can be defined on S? How many of these are reflexive? Suppose the elements of S are A, B. S contains two elements. Then numerics of S cross S, the elements of S cross S is 2 into 2, and which equals 4. And S cross S is given by A comma A, A comma B, B comma A, and B comma B. And B comma B. The elements of S cross S are these. So we have to find that the total number of relations on S. Any relations on S is a subset of S cross S. That is, any subset of S cross S is a relation. That is, which implies that the total number of relations on S equals 2 to the power 4 and which equals 16. Now we have to find out the total number of reflexive relations. It is given that we have to find out how many of these are reflexive. The total number of reflexive relations will form if any relations contains these and these two terms, then we will say that relation will be a reflexive relations. That is the relation if R is any relation and containing x comma x for all x belongs to S, then we will say that R is an reflexive relation. The definition of reflexive relation is a relation R is said to be reflexive if and only if for all x belongs to reflexive on a set S, that is a relation R on S. R is a relation on S said to be reflexive if and only for all x belongs to S, the ordered pair x comma x belongs to R. Then R is called a reflexive relation. To find out this, we will consider that these two elements as a single element, and subtract these two elements from the elements of S cross S. That is, S cross S has 4 elements. If we subtract these two elements, then S cross S will have only 2 elements. That is, we will consider after considering A comma A, B comma B as a single element and subtract these two elements from S cross S, then we get the total, we get the result as result as 4 minus 2 and which equals 2 total, and the total number of reflexive relation will be 2 to the power 2 and which is 4. Actually, what is happening here? Here S cross S has 4 elements A, B, B, AB and BA. If we subtract these two elements and find the number of subsets of the remaining containing these two elements, total number of subsets, if we subtract the first two elements, then S cross S will remain the last two elements, that is AB and BA, and suppose this is S cross S dash, or this is, suppose this is S cross S1, then the total number of subsets of S cross S1, that is 2 to the power 2, and if we include these two elements to all such subsets, then we will get all the reflexive relations. That is, the subsets of S cross S1 are phi AB VA and AB BA. If we include these two elements, that is these two elements, to all the set formed, all the subsets formed, then we will get the reflexive relations, all the such reflexive relations. That is, it will be as AB AA, it will be as A comma A, B comma B. It will be as A comma A, B comma B and AB. It will be as A comma A, B comma B and B comma A, and it will be as A comma A, B comma B, A comma B, B comma A. So there are 4 reflexive relations here: R1, R2 and R3, and this is R4. Thank you. Now we will try to solve question number 7.2. In this question it is given that, so that the number of different reflexive relations on a set of n elements is 2 to the power n square minus n. How does it? It is the universal case of the problem number 7.1. It is the universal case of problem number 7.1. That is question 7.2. Universal case of problem 7.1. Suppose S is a finite set having n elements. Suppose A1, A2, A3, An. Then Ns equals cardinality of n is n. Cardinality of S is n. Then S cross S has n into n, and which equals n square elements. N square elements. Similarly, as previous, we will subtract n elements A1 comma A1, A2 comma A2, 3 comma A3, An comma An. From where? From S cross S. Then it will contain n square minus n elements. And the total number the total number of subsets without these a1 a1 a2 comma a2 a3 comma a3 an comma an. These n elements will be 2 to the power n square minus n. If we add all these n elements, a1 comma a1 a2 comma a2 a3 comma a3 an comma an, to the subsets obtained then we will get the total number of reflexive relation as 2 to the power n square minus n. Hence completes the proof. Thank you. All are requested to make comment if there is any doubts related to the video and related to the problems.